Right, started recording. Hello, everyone. Glad to have you in the reading group today. Um, just a bit of introduction before I start the topic of this reading group. So, in the last couple of talks, last couple of sessions in the reading group, I have been focusing, started with some discussion on the transformer, and then again then after that with some NLP model. And recently, we started talking about some computer vision stuff or multimodal, in particular the clip model and the vision transformer, so the application of transformer in computer vision. And last thing, if I'm not mistaken, is a discussion about the clip, where you kind of link between text and computer vision. So you describe an image with text and then you match it to an image and something like that. And today I'm doing a little bit, I'm going through a different paper. So there's the one from Meta AI, recent one. I think they published it back in March this year. And the paper is about image segmentation. So this is an interesting research. We just opened the paper. So this is an interesting research from Meta AI, and just a heads up. So I just want to clarify that my main area is NLP. I haven't done a lot of computer vision, so I'll try my best to explain some of the stuff in this paper, but unfortunately I'm not super expert in this area, so I'll try to answer any questions, but some of them I might be unable to depending on the difficulty of the question. So the one interesting thing about this paper, and before I start, I just want to make sure that I just want so if you have any question, just feel free to write them in the chat. I think there's also the if you want to ask a question, or if you want to speak maybe later when we take some questions, you could there's like a request, which is currently there's no request, but in the meantime I will just be checking the chat every now and then in case if there's any question. All right, so let's go back to the paper now. So one thing interesting about, I mean, image segmentation is like, it has been being researched, I don't know, since forever. The one thing interesting about this paper is that it's kind of a foundational model, and personally I haven't been seeing a lot of foundational model in computer vision. I mean, again, I'm not the expert here, but most of the foundational models, when you hear about them, your mind immediately goes to something like ChatGPT, GPT 1, 2, 3, etc. These large language models trained on massive amount of data, available over the internet, and they start to develop some kind of like general understanding of how language works, and they adapt very well to tasks they haven't even seen. So this paper is like one of the foundational model in computer vision, and you can see the author clearly stating that their goal is to build a foundation model for image segmentation. And before I start jumping into the detail of the implementation, let me just show you the demo. They have an interesting demo. If you just close all the browser tabs, so if you just search on Google segment anything, you can see a very nice interactive demo. They provide you with some I don't know why this is not allowing me to accept. Oh, okay. Yeah, so they provide you with some images, and let's just pick one of them and see what kind of things you expect from this model. So you hover over this dog, and it automatically segmented. You can see it's highlighted, so it's detecting that the boundaries of the dog in this picture. You go back here to one of the trees, and you get the idea. So one of the the one thing that they want to highlight in their paper is that they would like to allow different kind of prompts So you could have a prompt by a point, just like in this case I'm hovering over a point, and then it tries to guess what the object you are hovering over is. They also allow you to do like a box, so you could give it a bounding box and it try to highlight the to try to segment the object inside the box. So let's see if how that will work. Okay, yeah, so I gave it a triangle and it guessed that I'm trying to segment the dog. So you can play with this demo, you can upload your own image, etc. And then later on I'll show you a demo that I did using the code, just in case you want to do your own experiment with the model. It's freely available, that's a good thing about it. Just checking to the question. Okay, no question. Right, so let's jump into the idea, to the contribution in this paper. So they contribute three things. They mentioned that the main contribution of this paper is three things, and they start by defining a task, and then a model and a data, which is natural in kind of like any machine learning area of research. You want to define your task, and the way they define their task is that they would like it to be kind of to help them in building a foundation model. So they want to try kind of the idea of foundation model is that you build a very massive, say for example language model, and then you could actually interact with the model in ways that it might not necessarily have been trained on. So you could say, when for example when you talk to ChatGPT, you could actually tell it you are, say for example, a psychologist talking to a patient, and then you give it a question as a patient, and then it kind of take that role of a psychologist and then answer the question. So they want to apply the same thing here, where they want to define the equivalent of a prompt in computer vision, and then they define their prompt to be, we will talk about it later, what we mentioned earlier in this example, like either a bounding box or a point, etc. And then obviously their task is that given like the promptable segmentation task, the goal is to return a valid segmentation mask given any segmentation prompt. So that's what you expect, and then the model is obviously what help you achieve this. So one thing that they mention is that obviously they want their model to be flexible prompts, and this is kind of like their way of trying to achieve a foundation model. They don't want predefined tasks. They want to they currently support a point, box, and text, but I'm guessing there's going to be further research to generalize this model or this line of research. And then the other thing they want to achieve is that they want it to be, in amortized real time. So you saw how we were able to execute it in the browser. So they state that one of their goal is to achieve to predict a mask from a prompt in like 50 milliseconds in a web browser. Now this is, I don't like this statement or such a statement, because when you say in the web browser, what exactly is the PC you're talking about? Are you talking about, say, an i9 Intel desktop, very powerful one, or are you talking about a laptop? It's a bit vague in this statement, and they don't say what kind of PC they use to web browser, but I think you get the idea. It's that regardless of what the browser is, it doesn't seem to have used like powerful GPU machine or on a server somewhere. Right, so and then the other challenge that they try to the other challenge they face is that when you talk about language models, you have all the data over the internet. You have Wikipedia, you have books, you have Reddit, you have as much data as you want readily available for any kind of NLP work you want to do. But unfortunately for their line of research in this paper, the data isn't available, because even though they find you could find like millions or billions of pictures online, and you can just use them. The challenge here is that you want to be able to get data annotated with masks. So for example, I can't just use a picture like this to train. Oops, I don't know what happened. I can't just use a picture like this to train my model, because I need to tell my model, well, here's a picture, and this is the mask I would expect you to predict. So that's kind of why you need like a annotated task and annotated data set, and this isn't available at the scale they want, because when you want to train a foundation model, you have to have a massive amount of data. So this is an interesting approach they did, where they built a data engine, and the idea is that they start with like a minimal data set. Well, maybe minimal isn't the right word, but a small data set, and then they try to they have like multiple stages where they have professional, what they call them professional annotators. I don't know how they define the professional, um, but basically human annotators, and then they help with the initial data, and then they train the model on the data, and then use the model itself to have more data, and so on. They call it like I think they called it model in the loop. So the model itself is used in the loop of generating the data. You train the model, you generate more data, and then so on, until eventually, long story short, they accumulated the data of 11 million pictures, and they have 1 billion masks. So that's pretty much, each image has 100 masks in it, and this is a massive data for training. The data is available, and I'm going to show you an example of what the data looks like. In fact, let's just go through a quick coding session. Not coding, sorry, just showing you the data. But I want to zoom this a little bit. I don't know how to zoom my terminal. Oh, I know now. Okay. So let's see. So that's the data. They called SA1B. I think this stands for segment anything 1 billion. So let's go. I just want to confirm that the font is readable. Can someone please confirm whether the text size is readable easily on the chat, please? Okay, just even on the safe side, increasing it a little bit further. Okay, right. So let's see. Let's open one of the. Let's see if I actually do. I have any? Do I have it here or not? No. Oh, that's. I don't seem to have it here. Uncompressed. Let's see if I have it somewhere else. No. Well, that's a bit unfortunate. I might have to download it later and then show you some sample. But it's essentially an image and then a JSON file showing the dimensions of different segments in the image. I'll see later if I have the data somewhere on my machine. Yeah. Alright, so going back to the paper. I just see someone typing, just waiting to see if there's any question before continuing. Okay. Right. So that's the data set, and then after that, let's take a look at the model just to see what the model isn't as difficult as the result it makes you feel it is. So scrolling a little bit, you look at the model. The model is has three main components. So they have the image encoder, and then they have the prompt encoder, and then the mask decoder. So the image encoder is as you would expect. So you get an image and then you do an image encoder. Now let's not spend too much time talking about what the image encoder is. It could be anything. It could be like a vision transformer. It could be any encoder for now. Obviously the quality of the result depends on your encoder. And then after that you have the prompt encoder, and this we will talk a little bit about. And then you have the mask decoder, and then obviously you would expect in this case, let me just zoom in a little bit. So this is a picture of a scissor, and then you would expect the output to be something like this, where it highlights, it has a mask over the whole scissor, or part of it, depending on where your point is. So that's kind of what the decoder functionality is. So the decoder is given an image encoder and the prompt, and your prompt could be points. So you could, for example, in this case, if I choose this point, then I would expect the model to highlight, this part of the scissor, or maybe, if depending on the ambiguity, the resolution, which I'll talk about in a bit, it's either this or or maybe the entire scissor, depending on what you want. And then the box is what we saw. So we will see later how they encode these things in the prompt encoder. And the text, and I think this is like still a preliminary research, but the idea is that you would want to we will see later in the paper how they mention some examples of actually using text to decide what to select. So you could say, for example, the image of the cat in the image, and then it should see the cat and then segment it. And the prompt, so let's talk a little bit about the detail of the model. I will talk about the image encoder later, because that requires some detailing. But the prompt encoder is depending on, they have two different sets of prompts. So they have the sparse one, which is either point or box or text, and they have the dense one where they select a mask. And this is kind of like a little bit more generic, because with a point you could just specify a point, with a box you could, well, just a box or a text. But what if you want to specify your own shape of kind of like, imagine, for example, when you're using like Photoshop, where you have like the free tool, you could select any area and then ask Photoshop to select some object within it. That's kind of like what a dense mask is. And they represent the point and boxes by positional encoding. So this is a standard thing in transformers, because you usually end up with embedding, which is like 500 dimension or whatever, and you want to have some kind of like special code to indicate this is an X dimension, this is a Y dimension, etc. And so that's why they present with a positional encoding and then summed with learned embedding for each prompt type. So if the prompt type is it's a point or a box, etc. And dense prompts are obviously have to be specified as like a whole image, because this is how you end up specifying which points you want in your image to look for segments in it. And that's why they have to use dense prompt is like a whole image, but they apply some embeddings, some convolutions over it to reduce the size of it. But we can see more details later in the appendices. Now let's talk about the image encoder. Just see if there's any question. Okay. Yeah. So talking about the image encoder, I want to show you just as a to refresh your memories, or for those who haven't joined the previous sessions. So I wanna go to the to the original, or to the first the vision transformer. So we walked through this paper in one of the previous sessions, and this is kind of like the first application of transformer on computer vision with good results. And you can see how the idea that we talked about is a basic one. They apply the usual transformer encoder architecture. You can see this one, but they apply it on patches of the image. So they split the image into multiple patches. The goal is obviously to apply to kind of like convert the image into some n-dimensional representation that identify the different meanings in the image itself. So the way they do it is that they convert the images into different multiple patches, and then they apply some linear projection, and then after that they apply some positional encoding, just kind of like they treat the different patches as a sentence. So imagine with a BERT model or any transformer encoder where you give it a sentence and then you get the encoding, and then your sentence has positional encoding for the transformer to know the relative positioning of the different words in the sentence. So the same thing here. Essentially, you're treating the different patches of the image as kind of the equivalent of words in a sentence. And then you apply the transformer encoder, and then you get the first head, which is the classification head, as kind of like what represents the image. So that's kind of the base architecture of the transformer vision. But they don't use a vanilla vision transformer in this research, in the segment anything model. They use a modified version of it, which is the masked autoencoder. So the masked autoencoder, let's take a look at it. It's this paper. So it's a similar idea to the vision transformer, and the main difference is that they follow a BERT style, where in BERT, for example, you try to mask some of the words, and then you try to make the model guess what that missing word or that mask word is. Similar to how, for example, you teach a kid how to language by masking one of the words and try to get the kid to know what that masked word is. So this is similar here, but the idea is to apply it to computer vision. So you give it an image, and then you mask multiple patches of it, and you try to train the model to guess what the picture is, what the original picture is. So you do the typical encoder decoder architecture, but then you mask some of the patches, and then you let the model guess what the target is. So what these authors noticed, is that they could actually patch up to 75% of the image. So you can see that you pretty much like most of the image are just masked, and you just have a little bit of some patches here visible, and then the model could guess it. And actually, we also could guess it as humans. We could guess that this shape, what this bird is going to look like, because we know from the color, etc. So they use this the masked autoencoder vision transformer, and one thing they gain from this is obviously the model is going to be better. I mean, I'm assuming so, because it learns how to guess what the picture is with a minimal number of patches. But then the other thing they gain is that they don't have to they make the model more efficient. So because you're only applying the encoder in the encoding phase, you don't apply the transformer over all patches. So in BERT, for example, they apply it, or they have a special token to indicate the mask token. But in the MAE model for vision, they don't actually do that. They just ignore it because they have the positional encoding, and which tell them where this patch is, and that saves them from computing 75% of the patches, and that make the model more efficient and allowed them to have more data. So I think if you go to the appendices, this is like a very long paper, which I don't think I fully understood everything in it. It's been a long time on it, and still there are some gaps on it. But if you go to the appendices, they talk about the model, the encoder in detail. And one thing they say is that encoder output down the scale, space. I don't know whether they say it here or in the other paper, but they say how reducing the number of patches and using a masked autoencoder allow them to use more data in the model and keep it less computationally expensive. So it's we're already 30 minutes in the reading group. So the reading session. So I want to actually go ahead and do some practical example, and then maybe I could go back to the paper and do more discussion, in-depth discussion. Just seeing whether there's any question at this point. Okay. So yeah, let's do some practical example here. I just want to show you how you could actually use the model. So I'm gonna use this picture I got from the internet. So it's I have an interactive notebook that I will use, and model is available online, as I mentioned. So let me try to grab you the link. Actually, I'll do that later. I don't want to waste your time. I could add that later in the Discord channel. But they provide you with multiple models. I'm gonna use the largest model and then load it. Just waiting for a couple of seconds, and then this is the image, just using OpenCV2 to load the image. And then I'm gonna, let's see what to choose. So let's try to give it a point somewhere or on this guy and see what it expects, what it gives me as the mask of this on this image. So that's roughly coordinate x 1000 somewhere, and then 200. Let's try to give it 1200 and see what it tells me. 1200, and then when you use it, they provide you with, actually, sorry, I jumped in a little bit earlier. So they provide you with the GitHub repository, which you can use to install the library. Assuming it takes a little bit, so you can install it with just by using their GitHub. But I actually, in my case, I have the code locally. I cloned the entire repository and then added a path to this folder in my machine, so I could do some debugging, I could trace the code, etc. But you can equally just use installed with pip and then give it the GitHub location. So importing it, they provide you with some helper classes that you could help you with building the help you easily employ the model to do segmentation. So I loaded the model here. In their registry they provide you with multiple model. Let me show you what these are. So SAM model registry. They have like I think this is stand for maybe basic, and then this one is large, and this one is huge. So they have 3 models. I'm using the largest one, and then now kind of opening an image, and then giving it a point and a label. So when you use the model, the predictor, you give it the image, and then what this method is going to do, and we will see it in the code, is that it's going to pre-calculate the embedding. Because the idea, as you saw earlier in the paper, they mentioned that they have the dataset section. They mentioned how they ended up with 11 million image, but 1 billion masks. So obviously there's like almost 100 masks for each image, and obviously you don't want to recalculate the embedding every time you deal with one image. So you calculate it once, and then you apply it 100 times for all the segments. So when you call a set image, it's actually calculating the embedding behind the scene to allow you to use the predictor multiple times on the same image. And then you can use the predict method, and what you give it is that you could give it a point coordinate, or you could give it a box. In this example, we're going to use the point coordinates. The point label here is allows you to specify whether the point is a foreground point or a background point. Excuse me. So I'm not actually fully sure I understand the purpose behind this, because for each point it's either going to be a background point or a foreground, and then when I try to give it in this case it's obviously a foreground point. So when I try to give it a foreground point and then give it 0 to kind of like see whether what it's trying to do, it gives me some response which doesn't make sense. So I don't know why they expected to specify this, but I could be missing something. Maybe something I need to somewhere in the appendix I missed. But anyway, in this case, I'm giving it a foreground point, so specifying 1 here. Let's comment this one out because we're not worried about the boxes now. And then defining the predictor, setting the image, and then doing a prediction. So let's see what it's gonna give me now. So it gives me back masks and scores and then logits. So let's see what the masks are. I usually take a look at the shape because that gives me an idea. And you can see this is the shape of the image. So 1192 and then 874, that's the height, and then it gives me 3 results. And the 3 result I'll talk about now, about the disambiguation, but let's see what this image looks like. So if I do let's do plotting. So if I do plot and then show one of them, PLT, I think that show, I think like this. No, I think I did something. Oh no, it's not image, it's mask. So you can see the mask here, but let's actually, instead of showing it separate, let's put it as an overlay over the image itself, which I have a function predefined here I could share later. So we show the image itself, the original one, and then show the mask, and then let's see what the result we're gonna get is. Okay, so you see it's kind of like it guessed this is the segment I'm looking for. Now let's see what the other masks are, because it gave me 3 masks, not just 1. So let's take a let's try the first one, and you can see it's covering a little bit bigger area now than the previous one. Let's try the last one, and it's covering kind of like the entire object now. And this is what they mentioned in the paper. So going back to the model, in fact, I think it's the task. So they want to let's see where the text I was looking for is now. Task. Okay, so they want when they define their task, they want the model to be able to deal with ambiguity. So the requirement for a valid task must simply mean that even when a prompt is ambiguous and could refer to multiple objects, the output should be a reasonable mask for at least one of those objects. And they give an example that a shared versus person, for example, when you try to when you have a point over the shirt of a person, do you actually want just the shirt or the entire person? And this is a similar in our case here, where you have a point over this statue, but are you looking for just part of it, which is in this case the head, or the entire statue? So that's kind of like where they train the model to give you multiple outputs, so that it's kind of like it disambiguate the output just in case, and it gives you a confidence level. Actually, I'm curious now to look at the confidence level values it returns in the scores. So scores, so it gives 91% confidence level to the head, and then 95% to this. In fact, I just wanna plot them all. Yeah, I don't know why it's giving. So it's giving this one the highest score, 95%, and this one it's giving it 91%. I think that makes sense to me. Like, why would you give like most of the back of the head but not the front? So that makes sense to me. But I'm not sure why it thought which I think it also makes sense. Like you know, if you're clicking here, you probably more likely want the head than the entire statue. But I guess this is just arguable. So, but the basic idea is that they want to give you some score for you know all the mass that it returns for you. So yeah, that's kind of like the basic idea of how to use the model. Now, obviously, there are more ways. In fact, let's try the bounding box. So I'm just gonna comment this out and then, oops. So the input box, let's see what we would like. Let's again try to aim for this shape here. So this time I'm gonna try to make the box such that it covers the entire statue, and then I want to see whether it, you know, what scores it returns to me. So we're talking about what's the maximum image size? So the image size is 1192. So I'm gonna go with 1150. That's gonna be the right point. And then before that, I'm gonna do like 900. So 900. 900. Let's see. 950, for example, all the way to, we said 1150 to say 500. So kind of trying to cover the entire statue, and then giving it the box, and let's see what it returns for me. So see again the scores, printing them here, and then let's print all the or display all the images. So now it's giving me a similar oh well, that's funny. It gives me something that is I don't know whether my segment, my box kind of does not cover the nose, for example. But let's see what the highest score is. The highest score it gives me is the last one, which I think makes sense, like because I gave it the entire box, so I'm more likely to want the entire object. So it gave this the highest probability, which makes sense. Let me see if I make the box smaller, so just to 300. I want to see whether it gives just the head the highest priority. So instead of 500, I'm gonna go with the 300, and then plot them again with the scores. So let's see what it gave me now. Did I plot everything? Okay, so interesting. So the probabilities are much closer to each other now. They're all 97, but the highest one is the second one, 97.47, which is the head, well, the hair without the nose, and this one is almost the same probability but less. What if I try to bring this a little bit further to the left to see whether that's, you know, whether my box is kind of like not covering the nose and the eyes. Okay, so plotted them again. Which one is the highest probability now? Highest probability now is the third one, the last one, which is, I don't know how it differs from the second one, but I think it's guessing it right. Now that I'm extended it to the left a little bit, it's catching the entire head. But yeah, anyway, I don't want to spend too much time on this one. You can, you know, it's interesting to spend time on, but you can probably do it on your own time. I don't want to take too much of your time. So I want to go back to the paper now, just in case there's a last thing I want to, you know, talk about. I mean, there's a lot in the paper, to be honest. I would encourage you to take a look at it, at the model. But there is one thing actually I want to do something quickly. I want to show you the code. I mean, it's very interesting how, you know, the code itself is is not huge. So if you go to the code base, you will see that there is the image encoder that we talked about, and then there is the mask decoder and the prompt encoder, kind of like the three components they talk about. And the image encoder, if you open this class, you will find that it's not a traditional transformer. So it is a transformer. It's the same idea. So for refresh, just to refresh your memory, I want to go to open the transformer paper, and then zoom in a little bit. So this is the transformer paper. This is kind of like the encoder decoder architecture, where you have the multi-head attention and then the feed forward network, and then each head is supposed to kind of like each the encoder is supposed to have each token attending to every other token. So if you have a sentence of n tokens, then there's n square minus n attentions. But in this model, they provide a windowed attention, which means that you don't attend to every single other token. You only say attend to a window of size. So if you have a statement of size 16 and a window of size 4, then each word only attend to the up to 3 tokens before or after it in the window it has. And then they do talk about this in the paper here in the model. Going back to the model. Oh, they don't talk about it in the main paper, but they talk about it in the appendices. So it's a little bit misleading initially when you read it in the main paper, because you imagine it's just a typical computer vision transformer with a mass autoencoder. But actually, when you read the appendices, they have a little bit more detail here. So they talk about motivated by scalability. That's what I mentioned earlier. Because the mass autoencoder only uses 25% of the patches of the image. And then other thing they mentioned here, that they pre-train vision transfer with minimal adaptation to process high resolution inputs, specifically VIT Edge 16 with 14 by 14 windowed attention. So it's not a global attention, but every 4 layers of the windowed attention, they apply a global attention blocks. So if you imagine the transformer layers to be like this, L2, L3, L4, and then all the way up to L12. I think they have 12 layers. So this one is going to be windowed attention, and this one again, and this one, but this one is going to be a global attention. I don't know how this happened. So that's kind of like the modified transformer architecture they use, and I think that makes sense because, if you think about the language itself, you could actually easily have the situation where a word at the end of the statement belongs to something at the beginning of the statement, and thus it makes sense to have a global attention. But usually with images, you usually have the attention related to the surrounding of the image. So in our picture here of the dog, there's a relationship between these patches and the patches around it, but there's no need for attention between, say, the leg and then this tree. They're just too far apart, so that you're more likely to have local attention working better than global attention. But they still apply global attention every 4 layers to make sure that just in case there's some relationship, like for example you have a car that is there's a driver at the top front seat, and there's kind of like a relationship between the car itself in the back of the car and the driver, because the driver is inside the car, etc. Anyway, I mean, there's a lot of details, but it's already like 50 past 7, 51 past 7, so I don't want to take more of your time, and I want to leave some window for asking questions. And I guess if there is more interest in understanding the details, the nitty-gritty details of the paper, then we could have a follow-up session, because it's huge, 30 pages. So I'm gonna open open it for questions now, and let me know in the chat or later in the Discord channel whether you would like to have a follow-up session to understand the details and go more in depth in the code. It's very interesting actually to to debug the code. This is one thing I did. I didn't find all the details in the paper, or at least it wasn't very clear. But then when I did debugging and then I went through the code line by line, it helped me understand the paper a lot more. So I'm gonna open it for questions now. I think there's like a button to request questions, and then you could be invited to the stage, or you can write your question in the chat. I see someone typing question. So the question is, does this also recognize what the masks are? For example, in your example photo, the dog, does the mask that outlines the frog recognize it's a dog? Oh, okay. So, I believe no, it doesn't. I mean, I didn't see anything that indicated it does. So it's not doing any kind of classification. It's just doing masking. Now, this is actually a good question, because one thing they talk about in the paper is that they are trying to do the goal which they mentioned is that they want to build a foundation model. So they mentioned that in their experiment, they talk about multiple experiment where they could integrate this model to achieve more computer vision related task, and just trying to find out where they mentioned this. So definition that we have not the foundation. Well, self-supervised. Yeah. Oh, yeah. I think that this is where they talk about compositionality. So they mention how, for example, the clip model. You train your model to have like the general pattern, and this makes the foundation model, and then you can actually compose it with another model to achieve something else that beyond what you trained your model for. And they use one prominent example is how the clip model that we talked about I think a couple of weeks back was used as a component in the DALE system. So while they don't actually tell you that this is a dog, this is a cat, it's very easy to have to get this foundation model, plug it with some data set that allows you to identify this is a dog, this is a cat, etc. Just like how, for example, with the BERT model, or any language model, you could easily have attach a head to the model to make it be, usable for, say, sentiment analysis, where you could apply it to Amazon reviews to know whether it's a positive review, negative review, etc. But yeah, the short answer is no, it doesn't recognize what the actual thing is. And if it's easier, you could, it's easier than typing, you could just I could just invite you to the stage, and you could speak. This on Hugging Face Space, which does this on video. Okay. that's helpful. It would be helpful if you share a link for others' benefit. Cool. So, if there's no other question, then we could perhaps end it. And then if you let me, I see someone typing. Let's see, the voice of pancakes typing in again. So just waiting to see if there's another question or okay. Meanwhile, I'm gonna share, I mean, links to maybe like later on to the notebook I wrote. It's a simple one. You could actually find other notebooks on the repository itself on Facebook Research. Um, but I will also share mine and then upload the video of this discussion of this reading group for those who are interested. Um, you can see the paper. It's a segment anything model, but I will also share the other paper I reference because there are a couple of kind of like very related papers to this one. Like the vision transform paper and the MAE paper, etc. I'm gonna share them all, and then share it with the group. How precise do the masks get? Like, do you think I could tinker with it to get to analyze each individual item and distinguish from the other background? So that's also a good question. This is actually one of the so if you go to the conclusion, they identify some of the limitations of this research. So while SAM performs well in general, it's not perfect. It can miss fine structures, hallucinate small disconnected components at time, and does not produce boundaries as crispy as more computationally intensive methods that zoom in. So I think the answer to your question is that it's as precise as many applications need, but it's not extremely precise if you're looking for something like at the pixel level for everything. So um, if that answers your question. Yeah, I mean, I think it's a step in the right direction, and based on the things that I tried so far, it seems to be working very well. But is it the best model for segmentation? I doubt. Just they mentioned this themselves, but it's certainly a great foundation model based on what they are reporting in their results. Cool. So it's 8 o'clock. So if you have, I'm just gonna wait for Doru Miro to finish typing. But if you have further questions, then that's the link. Thank you very much. Yeah, I'm gonna also include this link later. I just want to keep it here saved, but I'm gonna include it again in some message later on the reading group. But if you have further questions, please post them on the reading group, and then we can try to answer them. And if you have, I would like to, just before we end, I would like to encourage everyone to, like, this is an open reading group. Anyone could, if you have any paper that you think it's actually good to share with others, please do so. And then I just want to keep encouraging people to contribute as well. It has so far been mostly myself, but I want to encourage more people to bring their own papers. It's not, the expectation isn't that you have to be super expert with the paper you're talking. Just like you saw, I'm not expert in computer vision. I took this paper, I read it, tried to I got the code, debugged it, etc. But I'm not expert. I'm probably gonna be unable to answer many of the questions, but so I encourage you all to kind of think of papers that you would like to share with others and bring them on. Cool. Thanks everyone, and I wish you a great weekend, and looking forward to see you soon in another session. Goodbye for now.